Well, I think I'm going to go ahead and get started. Welcome back, everyone. I'm really very excited for this panel on sustainable built environments. I want to thank in advance Lauren Bowser from our Women in Aerospace group for monitoring our Q&A for this panel. I think hopefully the audience knows what to do at this point. If you're just joining us, please do submit those questions for panelists in the Q&A, and we'll get to as many as we can, both during the panel and then the panelists agree possibly through Huba after the panel. I now have the pleasure of introducing Daniel Kirschen, a professor in the UW Electrical and Computer Engineering Department. His research in smart grid technology strives to balance the three basic goals of power systems: reliable service, low cost, and integration of renewable sources by integrating communications, sensors, and controls to improve energy systems. He knows many of the challenges we face when building a stable power system in space. David, thank you for moderating this panel. I now turn things over to you.
Thank you very much, Sadia. It's a great pleasure to be moderating this panel on sustainable built environment. We have 4 great speakers lined up for you, and I'm sure it will lead to a really interesting discussions. Our first speaker this afternoon is Stephen Robinson. Stephen is a professor of mechanical and aerospace engineering at UC Davis. He's going to give us a tutorial on where we are in general on sustainable built environment in relation to space. He joined UC Davis after retiring from NASA after 36 years that included 4 shuttle missions, 3 spacewalks, lucky man, and extensive expertise in spacecraft systems, space robotics, and scientific payload operation. Stephen, the virtual floor is yours.
Thanks, David. And I get there, Daniel, 15 minutes, right? Can you hear me okay? I was asking, do I get 15 minutes?
You get a bit less than 15 minutes, so we have enough time for questions at the end.
Excellent. Sounds good. We'll see how far we get here. All right, getting set. All right, thanks for attending, everybody. I'm going to talk just a little bit about just an overview of most of the questions and the problems that a lot of people within NASA, universities, and industry and space around the world are addressing for sustainable environments in deep space. So let's consider a deep space habitat. What do we mean by that? We're kind of thinking of 3 flavors of microgravity. So it seems like you're floating, and that would be in orbit around something, maybe the Earth, maybe the Moon, maybe Mars, or in transit, or a partial gravity surface. The Moon has about 1/6 the gravity of Earth and no atmosphere. Mars has about 1/3 of Earth's gravity and not much of an atmosphere, and it's not one we're used to for sure. This spacecraft, you can envision being more than a decade in service. But here's what's really unique in the human experiences. It would not be entirely robotic, and there wouldn't be people there all the time. It would be intermittent crew presence. So maybe about 3 months every 2 years or so. And what we think of as mission control right now, back on Earth, there's many mission controls around the world. And it would be a very, very different function and expectation. And certainly, if you're far enough away, you have significant communications delay. So for a human-capable spacecraft, there's a lot of unique requirements, some of which come under the umbrella of spacecraft autonomy, which for human spacecraft we don't have much experience with. And the spacecraft should have the capability of learning as it goes. So learning systems are required. So we call this a smart habitat. But what does smart mean? Well, any space habitat has to guarantee the survival and safety of the crew and the onboard systems that keep them alive. And then you should be able to meet your mission objectives, the whole reason you went. So by smart, we mean progressively pervasive, onboard autonomy. In other words, it's changing, adapting, evolving, learning, getting better. But we do imagine that it's human supervised for the critical decisions. And so to have an autonomous or a largely autonomous spacecraft that can interface with humans, there has to be a sense of self-awareness that the spacecraft itself has to be able to maintain, has to be able to know and maintain its own state, also predict needs and take actions for self-sufficiency. This requires an optimal utilization of resources because you don't have much. You have what you're bringing with you in most cases. There is some possibility, depending on where you are, of in situ resource utilization, which is a hot research topic and will be for many decades as we learn to do things like mine water from the moon. If you have water, you can do many, many things, of course. But it's not just things like that. It's resources include your time, margin of safety, consumables, of course, ground and crew support capabilities, ability to reconfigure to take advantage or to avoid a developing problem. So this word evolving is pretty important. The capabilities of this smart hab should evolve to meet the mission objectives, which themselves will evolve over that 15 years. And I use the word optimal there. You know, when you think about optimizing something, you certainly have to have some predictive planning as an essential element. So we think of as an essential part of the smart part of a deep space human habitat as the planning is enabled by being able to predict system states and then respond to unexpected events. So when you boil it all down, you need broad capabilities in prediction and adaptability. Well, the top level is you've got to keep the crew alive while they're there and keep the spacecraft alive while they're not there, ready to accept the crew. Well, what do we mean really by alive? When you're talking about a machine, it can have a broad spectrum of meanings. When you're talking about people, not so much, pretty narrow spectrum. If you think about just the physiological requirements of humans, not even thinking about the psychological aspects of individual humans or their teams, but physiologically, you can see the kind of system that we know very well. We need atmosphere, waste management, food, water, and as closed a system for these resources as we can possibly engineer and make reliable in a spacecraft. Sustainability, obviously, when you're that far away from your resource sources, supplies, is an extremely difficult thing to do and extremely important because you may be able to do proof of concept, but making it reliable for that long and actually putting human lives on the line really ups the game. So the challenges are many. One is the logistics supply chain. There almost isn't one. You get a tiny little resupply every 2 years. For maintenance, repair, and overhaul considerations, well, the thing about going to space is oftentimes you're working with things that are almost serial number one. Lots of prototyping involved. So there's not much history. So especially in the environment that you're in. So you're likely to have surprises. There will be failures, and some can be quite mysterious because they've never been seen before. They will launch with limited operational experience. Ground testing will be done in, by definition, not the same environment. And you will have parts on board, most of the parts on board, don't have a legacy library of statistical failure knowledge. So what's the mean time between failures of something that's never known to have failed? So this is a very interesting set of problems. So you think about your system redundancy versus what kind of spares are you going to bring, how much volume and mass can you actually take with you? And the numbers are always way too small. And if you're going to have spares, then they need to be able to be installed during the times when the people are not there, which is most of the time. So now you have to engineer for robotic replacement. Robotic capability is not very good yet especially for things that the robot hasn't done before. Other challenges, I've said this a couple times, and it's just a very important part of how the spacecraft must always know its state and be able to conduct some sort of intelligent prognostics to look into the future, to respond ahead of time, not respond, but to act ahead of time rather than be in a responsive mode. Things can happen very quickly in a hazardous environment in space. Even when the crew is not on board, which is most of the time, humans will certainly be involved in critical decisions. Such a valuable asset will involve humans making the safety critical, mission critical decisions. But on board, since the people mostly won't be there, most of the actions will be taken by software controlling other subsystems like robotics. And as the spacecraft gets older, it will become less reliable, more infirm. Things will degrade in some ways that we know about and probably ways that we don't know about until we get surprised by something. To compensate for this, the software must learn. It must get smarter as it ages, just like us. To know the system state, the spacecraft has to have a very dense sensor system, and for anything critical for the sensors must be redundant, or should be redundant. Data analytics will be performed on board constantly, all the time. Most of the sensor systems will be fixed, also pre-engineered, installed before launch, some installed maybe after launch, especially if there's reconfigurations or added modules. But you have to have the ability to add sensors based on what you learn while you're during the mission, and that should be able to be done robotically. But these are the fixed sensor systems. There's also the requirement for mobile sensor systems. Go where they need to be. So they can be positioned by robotic agents of various sorts. They can be on surfaces. They can be out in volumes, behind panels where so much of the action in the spacecraft really happens. And you can think about it as a patrol where something is just always sniffing around, or directed. Please go find that leak over there. To cache all of this information, we are looking at the dynamic digital twin technology. So I'll talk about that a little bit more. And so when we're talking about autonomous systems, there sure are a lot of definitions of those. And so what our team has decided to go with is by Eric Frew at CU Boulder. Autonomy is the ability to perform complex tasks with substantially reduced human intervention. And autonomous system is an agent or system comprised of a machine being driven or controlled by some form of autonomy, but it always interacts with humans on some level. So in terms of foreseeing the future, modeling the future, and trying not to be reactive all the time, you can think of phenomenological or physics-based models that require dense sensor data, and stochastic or statistical models that require failure and degradation data from past experience. Initially, the spacecraft won't have much of that. By the time it's 15 years old, it'll know a lot. But of course, we're all diving into what I'll call observational modeling, machine learning based, where we question and try to validate its accuracy, its reliability. Where does the training data come from? And then when decisions or recommendations are made, is the process by which the AI function has come to some decision or recommendation, is that could be explainable to the human. For safety critical operations, the human is going to have a pretty good understanding, and it should be accurate. We have traditional engineering feedback control theory, where mostly we respond to errors. And the digital twin concept that I mentioned where for past information it serves as kind of a library or repository and constantly runs a set of models that are integrated for an intelligent prognostics. So it's kind of your crystal ball that enables sort of future thinking. So the vehicle management software or the crew or the people on the ground can be conducting constantly what if queries. What if I don't replace that vibrating part this week? I wait 3 months. What do my models tell me? So this all leads to the question of when do we use WISH, which is the answer is all of the above, of course, but at any given time, where do we put our concentrate our efforts or resources? And astronaut teaming with autonomous systems brings up some interesting questions. Does it imply there should be new requirements for astronaut selection if they're going to be on a spacecraft this far out? This alignment between actual state of the vehicle and what the vehicle thinks its state is and what the crew thinks the state is, how aligned should that be, and how will anybody know what that alignment is? If you're in a home that is changing its function as it learns, is that going to drive you crazy if it goes too fast? If it's different, if the coffee maker works differently tomorrow than it did this morning, yeah, that would drive you crazy. So there's some sort of modulation of that. Obviously, crew interfaces are really important, adaptable to individual crew as per their preferences or their learning or what they have forgotten. Crew procedures that are adaptable to the requirements on board. Lots of work going on that in that category. And it's not just the vehicle estimation and the software knowledge and learning. It's the state estimation of the crew. Humans change daily by the hour and by the year. And these are going to be long missions. So WARN sensors, various forms of external performance assessment, and feedback strategies to the crew themselves so they can self-regulate what's going on. Well, I've already done 15 minutes, so perhaps, Daniel, it's time to kind of take a pause and get some questions. Would you agree?
Yes, either that or we keep the questions asked. Lauren, do we have any urgent question in the chat?
I currently do not have any questions in my chat.
Right, so maybe we'll move on to the next speaker and then we'll have questions at the end. So our next speaker is Noel Schulz, who is a co-director of the Washington State University PNNL Advanced Grid Institute. Her research focuses on power systems modeling and analysis, smart grid application, microgrids, renewable energy, and shipboard power systems. Noel, the floor is yours.
All right. See if I can, there we go. Can you see me okay?
Yes,
Yeah.
and you can hear
Okay.
me fine.
Thank you, Daniel. So I had the honor of having a class from Daniel Kirschen at University of Minnesota a few years ago when I was a PhD student. So it's fun to be on here. And it's really an honor as to have a chance to be here as a power engineer in the land base to talk a little bit about synergies related to space, sea, and land for sustainable built environments and what we want to talk about in that. So I took a little different perspective than probably some of my other colleagues here, but so to think about it, first off, I started thinking about having the honor to be part of this. I started thinking about the synergies across the space, sea, and land technologies and how it's related to my career across. And I started thinking a lot about the space shuttle and how it really impacted me as a high schooler and doing some, the science around that. And I think my career today is partially because of the space shuttle and being excited about that growing up and the activities there. But I also think when I start to think about environments, sustainable environments, and we talk about sustainable energy sources, the alternative energy sources that and looking at solar for some of the space activities and really how it provided an opportunity for technology to advance that later would really be helpful for our land-based or terrestrial power systems. Then I had a chance when I was at Mississippi State University from 2001 to 2009 to work on the all-electric ship. And the all-electric ship was a ship that we were trying to make it reconfigurable. But as I look at both the space and sea applications, they're islands by nature. They're microgrids by nature. They can't connect in. Obviously, at space stations and ports they can, but in general, they're operating in cases where they have to operate as an island from a power perspective. And so in thinking about this microgrids and thinking about reconfiguration is something that was really important. And looking at alternative energy sources, as we looked at solar, as we look at both ships and space aircraft on alternative energy, nuclear and other sources that can be used. And then I thought about the land and terrestrial power systems. And as we look at this in this DOE graphic, a lot of the different aspects of it, whether it's renewable energy sources, it's about the environment. We also, in all three of these, start to see the cyber-physical interaction, that now it's not just about physical systems, such as the power grid, but also the interface with communications, with controls, and all the different aspects that my colleague was talking a little bit about, and even artificial intelligence as we're seeing there. But also as we start to look at land solutions and we're looking at terrestrial power systems, we also need to look at low-cost solutions. And in addition to reconfiguration, we talk a lot about resiliency. And so as I looked at this and thought about this a little bit more in the sustainable build environments and some of the engineering challenges and solutions we have, I thought about this picture that is from an institute consortium that's at WSU that's looking at it's called CHARGE, or the Consortium for Hydrogen and Renewable Generated Electrofuels. And what I really thought about this was the system of systems that get involved when we start to talk about solutions in a sustainable environment. And in this particular case, I think it's so important as we talk about in the case of electric vehicles or creating electric transportation, but that creates stresses and strains on our electric grid. We also look at alternative fuels that can be in a sustainable environmental front of something that we can do. And this particular picture, I think, is so interesting how it shows renewable natural gas, how we might use that, hydrogen, and actually using hydrogen possibly for renewably produced hydrogen for whether it's ships or terrestrial vehicles and things like that. But I think this really came as we talk about these systems in land, sea, and space, of the interdisciplinary nature of this and how it really has created opportunities for us in a very exciting time where a lot of the challenges are along the boundaries of what we do. And so I wanted to talk a little bit about a couple of the solutions, a couple of the different activities that I'm involved with that I think relate to this and can relate to some of the solutions, whether it's a space solution or a land-based power system solution. And first is we're collaborating with the Pacific Northwest National Labs. In 2018, WSU stood up three different institutes, and I think they all have opportunities related to space solutions. It's just finding the right way to make those connections. And I'm co-director of the Advanced Grid Institute. And really what we're trying to do is look at complex power systems for the future and look at the workforce. And those power systems could be on a ship, they could be in a space vehicle, they could be at a space station, and they could also be on another planet and looking at what are the different resources that we have there in the future. And bioproducts, as I talked about, different fuel sources. And so we're looking at that as an opportunity on how do we move forward to advance the power grid. And our particular efforts are the electric grid, but I think there are lots of applications in this, as I've talked about a little bit before. The other thing, we recently went through a strategic planning exercise, and some of the assumptions we looked at on external factors and thinking about our sustainability and some of the systems of systems. You know, a lot of different topics here, a lot of topics from today, whether it's workforce, whether it's equity and social justice, you know, energy that you've talked about as well, and across the day. And so there's just a lot of synergy across some of these different fields, and we don't always interact. And, you know, I appreciate this opportunity to learn today from the speakers, but also have a chance to talk about how could we work together on some of the solutions on the land power grid might be things that we can work in other space, in other areas such as space as well. I also wanted to mention another project with the Department of Energy that WSU helps lead called EECS, which is a US-India initiative. And, you know, I think this project, what we're trying to do in this project over 6 years is try to advance the advanced distribution system. And that is in our terrestrial power grids. But how do we look at storage? How do we look at renewables and integrate them into the grid? And so there's a lot of challenges here. This is actually a picture of the ladies in a village in India that are going to get electric power because of this project. And what I think is really unique about this project as we talk today is the fact that in India, we're building new microgrids, we're building new distribution systems, where in many parts of the US, we're trying to take old systems and redevelop them. And I think that's important as engineers to look at how would we do something from scratch, particularly as we might talk about space electrical systems versus how we already do it and changing that system from what it is and the paradigms that are there. So it's really an interesting thought to think about the differences between India and the US, as well as some of the other differences in policy, regulations, and how do we manage those across international boundaries and what we're doing in these solutions. This just shows a lot of the different partners we have across the US and across India working on this project. And, you know, I think as we talk about these energy solutions, whether it's space, land, or sea, it really is an international perspective on how we're moving this. And by working together, we come up with a different set of solutions. And the diversity of thought, the diversity of experiences through these international collaborations are so important as we move forward. So with that, I just wanted to kind of open the floor a little bit about those activities, and I look forward to talking more and answering any questions that may come. So thank you so much for the opportunity. And as a WSU faculty member, I have to say, go Cougs. So thank you very much.
Thank you very much, Noel. I don't think we have any urgent questions for you, so we'll postpone the further questions to the panel discussion at the end. So let's move on to our next speaker. Our next speaker is Heloise Vertadier. Heloise is a project coordinator for the Orbit Lunar Foundation, where she works in digital aviation and space law. Heloise, please go ahead.
Yep. Hi, everyone. Thank you, Daniel, for the introduction. So I wanted to talk today about, you know, how do we achieve the sustainable built environment and what is the first step to do that? And I have been involved with Open Lunar as initially as a fellow and now as a project coordinator of Breaking Ground, which is the project I will present today because it fits with that mentality of what is the first step to take in order to achieve that goal. So the goal we have is to try to find new ways of managing lunar resources. And so how can a perpetual purpose trust can be one of the viable solutions? So the perpetual purpose trust that I will talk about is Breaking Ground. And the reason why we created this initiative is because, as most of you know, the interaction with the moon will become more regular as we go. And even today, there's already missions going there in order to extract some moon rocks in order to, you know, look at it from a scientific perspective. But in the near future, it will be to create habitats, etc. So how can we create create a management regime for lunar resources which will be sustainable? So the Outer Space Treaty does prevent any national appropriation of outer space territory, but with the Article 2. But despite that, as we've seen in the last few years, there are some national initiatives about commercialization of lunar resources happening. And with that in mind, there is a power shift between the traditional actors, which are the space agencies, towards the commercial actors and commercial activities in order to manage and use lunar resources or resources in space in general. So there is right now a need to find innovative solutions. And the reason why we want to create those solutions now is to not be a step back, but to take initiative and create these solutions now in order to prevent any sort of tragedy of the commons that we can see on Earth. So what is a perpetual purpose trust or a PPT? So I don't know how many of you are familiar with a traditional trust, but usually trusts hold assets for the benefit of a designated party. That party could be a person or a company. But the difference with the PPT is that the beneficiary of the trust is its purpose exclusively. And so with that, our purpose, the legal purpose, which is in our legal document, is to steward and demonstrate formal and effective institutional management of lunar resources between different stakeholders. What it means is that the purpose and the sole purpose of the trust is to find these solutions that I mentioned before and nothing else. So there will not be a designated party as a person or a company. It really is about the purpose only. So how does it work and how does a PPT operate? So we have a trust stewardship committee, which is, if you want, the equivalent of a board of directors for a corporation. And in our document, we created 5 trustees representing the following viewpoints. So we try to have as many viewpoints as possible and be as interdisciplinary as possible. So we have an industry viewpoint, a science viewpoint, civil society, diplomacy. And what we decided with the 5th seat is to have it open in the sense of the 4 previous trust stewards or trustees will be the one defining which viewpoint that 5th seat will represent. And that is just to have a flexible and adaptive organization in order to be able to just adapt to what is going on and the different missions. There is also a trust enforcer in a PPT, which is the very interesting part of that format. The trust enforcer, if you want, is like a judge kind of position. It's an independently appointed role within the trust. So the trust enforcer is completely independent from the decision making. The person doesn't have a decision making power whatsoever. And the goal of the trust enforcer is really to assess the actions taken by the trust stewardship committee and see if these actions respect the purpose of the trust. So in a simpler format, how does it operate really? So there is a settlor, in our case it's Open Lunar, who created Breaking Ground the trust. And the trust Breaking Ground is run by the trustees that I just mentioned, so the 5 roles I just mentioned. And as you can see the trust enforcer, which is on a separate side because it's independent, it's an independent role. And the trust enforcer is that overarching authority that will verify and check if the actions taken by the trustees and the trust eventually do respect the purpose. And if it doesn't, then it becomes illegal. So we open ourselves to, like difficult situations. So why would a trust or a PPT be fit for managing lunar resources? I think the first aspect and the main aspect is really the legally enforceable and accountability mechanism that we have with the trust enforcer. So that's really an independent role that will make sure that the trust doesn't take a direction that will not respect the purpose. For instance, for the benefit of the trustees or anything like that. It's really that overarching judge kind of authority. It's also an independent organization, which doesn't have to wait for international agreements. As we all know, it's very difficult to take decisions on the international level, especially in the context right now for space. So with that action and with that organization trust, then we can take action before we reach an agreement, which can take years. It's also an opportunity to prototype new approaches for resources management on Earth as well. So the different solutions that we will find with the trust can be also applied on Earth, for instance, for water management or forest management. And it's also a new type of institution that really focuses on stakeholderships and which allows to create a consultative processes with subject matter experts. So these are the 4 reasons why a PPT would be a good fit for managing lunar resources. The other unique value of using a purpose trust is that it's a unique formulation of fiduciary responsibility. So even within the trust world, the PPT is a specialty in itself, and it supports a wide range of activities. For instance, with from charitable perspectives and purposes to for profit or or non-profit. So it's really very flexible, and that helps us with our purpose. And with that in mind, and because of that, we decided with the trust to purchase small amount of regolith. So we are following the lead of NASA, which published almost a year ago now in December 2020, a list of 4 companies that they allocated contracts with in order to purchase small amount of regolith. And so we followed that lead, and we are also purchasing regolith, and we will try to adapt the policy that we will find to that regolith. So really, like, it's a pragmatic use of it. And to find these policies, we won't do it by ourselves. We created a deliberation process, which is called the Deliberation on Our Resources Rights, or the DOOR process. And this process gathered together a wide range of people from different backgrounds, from different disciplines, from different cultures, in order to help finding those frameworks, as I mentioned, for breaking ground to use. So this is really an international deliberative stakeholder engagement process that we created in order to provide unique views and participate into the debates on the international level of what do we do with that regolith in order to create sustainable built environments. And the goal of that deliberation is to write a report that the trust breaking ground will use at next year in 2022 in order to apply the solutions that the group will find to the purchased regolith. So for instance, if we have 3 samples of regolith, then we can have 3 different solutions and 3 different management regimes that the DOOR process will find. We're currently holding the DOOR process, and we have delegates from each continent and all over the world. So the principles of breaking ground and how they influence the DOOR process, we really want to focus on multilateralism. So making sure that all nations and organizations can be represented as much as we can. We also want to create a responsible care of the moon. And with that, we want to avoid creation of monopolies. So we will advocate for fair competition as well, with a plurality of solutions, as I mentioned. And we think that the most important part of it as well is the adaptation and adaptabilities of the policies. So that's really something that we have to keep in mind. And we want to cultivate a shared sense of purpose as well with the moon. So what we are trying to do with breaking ground is not to create the solution or be the universal solution. We want to prove that different solutions can happen. And we want to demonstrate that a model based on multilateralism and bottom-up approach can work in today's approach. And so we really are trying our best to welcome as many voices and points of view as possible. And we reaffirm the fact that the moon has a special place for each person in every culture of the world. And we want to be respectful of that while also enabling innovation and commercialization. So with that, thank you very much. And I don't know if there's any questions.
Yes, I believe we have some questions for you. So Lauren, would you like to read the first question?
I would love to. So the first question is asking if you can see ADMS approaches like volt bar optimization or FLISR/resilience restoration being a part of that SMART approach.
I think that's more of a question for Noel.
What was that again?
Yes, I can reread.
Why don't we wait and we can do that one at the end? So
Okay.
if you've got one, go ahead, and I can do that at the end.
All right. For Heloise, I have, with the U.S. Artemis program and the China-Russia planned International Lunar Research Station, what changes in policy, technology, and mindset are needed to ensure sustainable lunar exploration and systems?
So that's a big question. I think what we're trying to do with Breaking Ground is really to take it step by step. So starting with what we call the teaspoon of regolith. With the Artemis Accords, it's a new way also to sort of open a discussion and a debate on the international level. And it's not necessarily our focus. Our focus is really to target the next term and near term missions that will go to the moon, and to just prove the management regimes that we will find with the door process. So that's a bit of a bigger picture. What we're trying to do is trying to be as independent as possible from nation states and international debates. And we want to really focus on that bottom-up approach in order to, see a different perspective from how we've been looking at space issues and space policies since the beginning of the discussion.
Thank you. And I think there might be one more question for Heloise. Lauren? I think Lauren is muted.
Thank you for telling me. I was reading the question and no one was hearing me. All right, so this one says, how do you see trusts like Breaking Ground evolving over time as space exploration and larger international projects take place?
That's a great question. So the way we created Breaking Ground is to be open sourced. So hopefully what we can think of for the midterm future, I would say, is that eventually similar projects like that could evolve around the world and involve different stakeholders and maybe have different purposes as well, in order to cover as much ground as possible. So we're really open source. On our website, you can find the creating documents and the process of how we created it. So if, for instance, anyone wants to create a similar approach and use a PPT to tackle another issue and have another purpose, then that would be the case. So I think it's really advocating part of it that I can see in the future for Breaking Ground, and hopefully why not, being the standard setter, or, but really what we want is the multilateral approach. So being that one single entity creating the standards is not necessarily the approach we want to take.
Okay, thank you very much, Heloise. Let's move on to our fourth speaker. Our fourth speaker is Emma Lehnhardt. She's a Gateway PP&C manager for the Johnson Space Center, where she leads a team responsible for the business operations of the Gateway. Emma?
Hello, as I am bringing my screen up, could I please get a comm check?
Yes, we can hear you.
Okay, great. Thank you, Daniel. All right, I am happy to join y'all today. Hello from Houston, Texas, where, yes, I work on the Gateway program, which is a part of NASA's Artemis program. Really happy to have received the invite to join this symposium. I did not attend the University of Washington, but can perhaps thank UW for my existence. So that's where my parents met and fell in love. I grew up in Washington State, so happy to meet you all virtually and looking forward to the questions. When NASA talks about Artemis and we use the word sustainable, we use that word in a couple of different ways. So I will spend some time today giving an overview of the Gateway program and Artemis and touching on some of the ways we talk about sustainable and sustainability. The Artemis program is NASA's program to return to the moon. We are planning on putting the first woman and the first person of color on the lunar surface. This is a NASA-wide enterprise that includes multiple programs like mine, the Gateway. And here's the first place where we use the word sustainable. When we talk about Artemis and long-term plans and the horizon goal of Mars, And this return to the moon, we're talking about going to stay, going in a different way than we did with Apollo, and developing a long-term presence on the lunar surface and in lunar orbit. I forgot to turn off the automatic slide advances that are timed, so bear with me if I have to catch myself if it advances a little bit. The Gateway itself is a small space station in orbit around the moon. I like to think of it as our first outpost in deep space for humanity. We will build this up piece by piece over time, and it will allow for an aggregation point of vehicles, a jumping off point for vehicles taking crew down to the surface of the moon and back up again. And it will be a test bed for all of the science and technology developments that we need before we take that next great leap to Mars. Stephen did a wonderful job at the beginning of the panel talking about all of the things you need to think about as you are developing deep space habitations and capabilities. And here's the second place I'll touch on Gateway and sustainability. There are specific things that we are doing with this vehicle that are inherently or meant to be sustainable. The first is its orbit. It operates in an orbit around the moon called a near rectilinear halo orbit, which is a 7-day elliptical orbit around the moon, which is a sustainable orbit. You can think of it as it's a stable orbit that doesn't take a lot of fuel to maintain. We are developing this space station to have a 15-year operational life. I think you heard that figure from Stephen at the beginning. And we are using solar electric propulsion to generate power and thrust for the entire station. The third way we talk about sustainable built environments and the Gateway and sustainability is with partnerships. And by partnerships, I mean both commercial and international partnerships. And just personally, that touches on, for me, the idea of political sustainability. This is a graphic of the full integrated Gateway spacecraft after we've built it up over time, with contributions from NASA with our commercial partners like Maxar Technologies, Northrop Grumman, and SpaceX, as well as contributions from our international partners, the Canadian Space Agency with a robotic arm and external robotics system and components, the European Space Agency with a habitation module and a refueler module, and JAXA, the Japanese Aerospace Exploration Agency, providing components with ESA for that international habitation component, as well as the European service module for Orion. We have not yet determined a partner for our airlock on the Gateway, but we are pursuing an international partnership for that as well. Hardware is being built today. I know Gateway is still a relatively new program, but in 3 years, we have made tremendous progress. And these are a few of our pictures showing on the left-hand side, the first habitable volume of the Gateway is called the Halo, Habitation and Logistics Outpost. And this is the primary structure of Halo being manufactured in Italy. And for our power and propulsion element, you can see some of the solar array power modules there, and the roll out solar array boom, which will allow the solar arrays after deployment, after launch, to roll out. Very cool technology. I was going to keep this short and sweet today because I really love interacting with my fellow panelists and getting questions from the audience. If you'd like to follow along with our journey, you can go to nasa.gov/gateway or follow us on Twitter and Facebook. So Daniel, that was short and sweet, and I'll stop sharing and turn it back over to you.
Thank you very much, Emma. Let's see, we don't have any specific questions for Emma, so maybe we can go back to the question that was asked, that was for Noel. Maybe Lauren, you can repeat the question.
Absolutely. So the question directed for Noel is asking if you can see ADMS approaches like bolt bar optimization or FLISR/resilient restoration being a part of that SMART approach.
Yes, actually, I just had a defense earlier today where we were working, the graduate student did volt-var optimization and looking at smart grid, looking at microgrids and looking at controlling. And so, yes, those are definitely solutions for our terrestrial system. And I think there will be sister solutions in some of the activities in both sea and space activities. And, as we talk about the terrestrial power grid, I thought, that can also be all over, grids, but there'll be different specifications as we talked about different build environments that we need to do. But yes, the ADMS and looking at how do we have so much more information on the distribution grid now than we used to have. And so we have a lot more insights and we can look at a lot of solutions. And AI, we're looking at machine learning, we're looking at data analytics. So a lot of those solutions are going to help us add to what we already do in the controls environment. So yes, I'd agree with that. Daniel could also probably answer that.
No, I think you know more about that topic than I do. Thank you, Noel. I think we have a question for Emma.
So the question for Emma is asking, what are some ways the gateway is mechanically sustainable in terms of replacements, damaged hardware, or improvements, and how have these ways improved over the years?
That's a good question. I think I'll try to answer that in 3 parts. First, right now we are doing what we call long lead procurements, purchasing critical components and doing those in batches so that we build up a common hardware pool for hardware that will be used across all of the elements of the gateway. The second is that, when we think about a 15-year operational life and the maintenance required for that, we do recognize that we will likely need to conduct astronaut EVAs, extravehicular activities, just like we do on space station today. As I touched on the airlock, that means we will also need new spacesuits and all of the resupply, training of crew, everything that goes along with the crew conducting maintenance on the outside of the spacecraft. And the third, I'm going to pivot a little bit and talk about instruments. So one of the things that still blows me away is that on the outside of the gateway for the Canadian robotic arm, we have pathways and hardware fixtures that will allow the arm to take a new experiment out of a science airlock, walk itself around the outside of the space station, and install a new scientific experiment in a fixture. So that is something that we will be able to continuously do even when crew is not present. I hope that answers the question. Thank you.
Thank you. I have a question for Stephen. We all follow the progress of the Mars rover and that. I realize it's a bit of a different problem, but what can we learn from things like the Mars rover that might be applicable to those more deep space exploration?
Well, many things. There's no spares at all. There's no repairs possible on Mars, and every time you want to talk to or listen to the rover, you have up to an 18-minute time delay. Imagine how annoying that would be to try to talk to somebody through something complex. And so NASA, JPL, and contractors and universities have done a fantastic job over the decades learning how to do this. And this is this mix I was trying to talk about, where you have more than automatic, you have an autonomous vehicle that actually takes in information about itself, its surroundings, and its mission, and makes decisions that are not pre-programmed, but are hopefully the best decisions. And it's, one kind of autonomy. Now, of course, if things don't go right, it has to be smart enough to say, okay, this isn't working out. I need to stop and maybe phone home and go ahead and wait that time. So we've taken a lot, for human-tended spacecraft, we've taken a lot of lessons and still are. And I think the autonomous systems and how to work those in with humans is one of the big learning points.
Thank you. I believe we have another question for Heloise.
Yes.
All right, so Eloise, the question is asking, how do you anticipate that fully commercial lunar facilities for the resource exploitation or other purposes will interact with the breaking ground organizational structure?
So for now, Breaking Ground is really focused, as I mentioned, on the teaspoon of regolith. So I guess that's just me guessing, but I guess for the organizational structure of the trust, we would think about expanding and having eventually more trustees and members of the Trust Stewardship Committee. We could also think of organizing more deliberation processes and this kind of thing. So I guess just a classic, for us to expand, but really right now we're focusing on really that teaspoon. That's why we have a rather small structure. So that would be my answer.
Thank you. And I think we have another question for Emma.
All right, this question is asking, what is the plan for Artemis at the end of Gateway 15's years? And NASA talks about going back to the moon to stay. Does that end after Gateway or transition into something else?
Great question. So Gateway is designed for, let's say, at least a 15-year operational life, just like the International Space Station today, which has been permanently crewed for now 21 years. As long as it is safe and operable, I would imagine we would continue operating the Gateway. And that's important because in order to develop the capabilities and test things out for future missions to Mars, where you have a multi-month journey to Mars in a microgravity environment, deep space radiation environment, a journey to the surface, back up again, and then another multi-month deep space microgravity journey home, we would like to be able to use the Gateway to test out those systems and perhaps even do a full analog of that type of a Mars mission closer to home. So that would require future build-up, expanded capabilities of the Gateway, particularly larger habitable volume. And correspondingly, on the lunar surface, NASA's current plan is called the Artemis Base Camp, which is a buildup of systems at the lunar South Pole to include habitation, unpressurized and pressurized rovers, all the things you would need for a full base camp on the surface of the moon. So those two pieces in coordination and working together would be our future plans that will allow us to use the moon to its full capacity to test out what we need to do for Mars and go there to stay. Thank you.
So if I can follow up on that, I realize, you said 15 years is just a target, but what factors go in choosing 15 years as a target for the life of such equipment?
So that's the design requirement for the spacecraft, and I believe the primary driver was thinking about the time needed to build up and launch and dock all of the components of the Gateway, which will need to be done over the course of several years. We launch each piece at a time, with the exception of our first two, which will launch together on a single commercial rocket, a Falcon Heavy.
Thank you. I think we have another question for Heloise.
Yes, this is my last question I have. It is asking, Article 1 of the Outer Space Treaty says that all people should benefit from exploration in outer space. How does your work on trusts address Article 1?
So that's a great question, and that's exactly what we're trying to tackle with the DOOR process, the deliberation process that I've mentioned. So the trust itself will participate to the processes, but the reason why we created the DOOR process is really to have a neutral, international, and interdisciplinary approach to these questions. And one of the main questions raised by the delegates is about benefit sharing and what does it entail. Is it an economic benefit sharing? Is it sharing of data, etc.? So we're in the middle of the deliberations at the moment. So I do not have a proper or tangible answer to tell you at this point, but this is definitely the core of the deliberations as of now.
Thank you. So I would like to encourage the audience to put more questions. And but let me ask a follow-up question to Heloise. We have a number of engineers and other scientists in the audience who may not be particularly familiar with trusts. Can you give an example of a PPT that might be a bit more easier to understand than the one you were describing?
So the PPT I described is really the classic structure at its easiest. So it's a rather new and innovative structure of trusts. I believe that Facebook has a PPT as well, but a much more complex and bigger one. So in order just to make it a little bit easier, just the only thing that you have to remember with the PPT is that there is no, the beneficiary is the purpose. So the only actions that Breaking Ground will take are to fulfill that purpose. So finding new and innovative solutions to manage lunar regolith. These are the only actions that the trust will ever take. And so that's why we have a broad range of possibilities ahead of us with that, including creating a deliberation process, as I mentioned, or managing regolith in a charitable way with benefit sharing at the core, or having a more scientific approach and give it to scientists, etc. But that's the goal of the deliberation processes. Really with the PPT, the only thing to keep in mind is the fact that any action that the trust will take will be to fulfill the purpose.
Okay, thank you very much. Lauren, do we have any more questions from the audience?
I do not have any more questions.
Do any of the panels have a question for the other panelists?
Yes, I do for Emma. When Emma, when one of the questioners was asking about the sustainability of the structures, space structures, would you talk about onboard manufacturing as part of Gateway?
So I do have to admit, Stephen, so I have a space policy degree. I am not
Okay.
not an engineer, but we are so for on-orbit manufacturability, we are demonstrating things on the International Space Station today, like 3D printing, which I am sure would be applicable on Gateway. But you know, when you were given your presentation, I was thinking, wow, this sounds a lot like many of my program board meetings with all of the things that we wrestle with and the technical details, but I have not heard us tackle onboard manufacturing yet.
It's certainly going to be part of the equation for sustainability, is to be able to build things where you need it, when you need it. But it sounds a little too good to be true in a lot of ways, because if you think about for spaceflight aircraft and medical equipment and many other things, if you build something, you don't just take it off the machine you built it on and put it into use. You now have to measure it, test it, qualify it, certify it for use in a safety critical environment.
Absolutely.
And,
yeah.
That's really one of the challenges of doing that in space.
Yeah. I can take a page from my husband actually here and jump off of what you said there. My husband also works at the Johnson Space Center. He works for our human research program on developing exploration medical capabilities. And one of the things that his group is trying to do is infuse medical design into the design of the spacecraft itself. And what that really looks like is things like, you already have water on board. Can you use the potable water on board to create IV fluids instead of flying up IV bags every time with a resupply mission? And I don't believe anyone has ever done that before. It sounds like a great idea, but that's one of those things where it would have to be absolutely tested and certified in this case, a deep space environment before we deployed.
Stephen, you mentioned digital twin, and I found that very interesting, and because it relates to, I think, the kind of stuff we use to run the power system. Could you elaborate a little bit more about what you mean by that?
Yeah, digital twin is a term that is used in many different ways and means different things to lots of people, kind of like autonomy, you know, or AI. The way, and when I say we, in this case, who I'm speaking about is the NASA Space Technology Research Institute, called HOME, which stands for Habitats Optimized for Missions of Exploration. And it's about 75 people total, mostly with universities, 7 different universities, and I'm the director of that. And part of the effort to both keep track of a changing space station that is going to be evolving over a long period of time is to have some sort of repository of information, but not just that, not just a library, not just a GIS-like database, but have it also be able to link to all the different modeling capabilities you're going to have on board. If you're modeling, say, carbon dioxide removal, that's a certain type of modeling process. If you're modeling wear on a bearing in a rotating machinery, completely different model. But the digital twin has got to be able to both keep that data, that information, look for correlations, and feed them into prognostic capability so that I can say, okay, a digital twin is the place where the state of the vehicle is. And I want to ask it, what state will I be in a week from now, knowing that I've got degradation going on in every single system. And okay, that doesn't look so good. Let me change something. I'm going to turn off this pump, or I'm going to take it down to 40% of its capacity. And now, what state will I be in a week? To me, the whole idea of this what if capability to ask my library of knowledge is what we envision as a digital twin in this deep space habitat.
So if I understand what you were saying, it's not having one big simulation of everything, but having separate detailed simulation of various aspects.
Yeah, we would love one big simulation of everything, including the people on board.
I was going to, my point was going to be that then you have a problem of the interaction between those systems and how you model those interactions.
Yes, that is exactly right. And some of those you model them, and some of them you do it from a control systems point of view. It's where you input a changed parameter. Could be a step function, could be a sine wave or something like that, and you watch the results in the other systems, how they respond. And so that's part of the learning process.
Are there any further questions from the audience or from the panelists for each other? Well, then I will ask a question. I think Emma and Stephen both used the word reconfiguration, and I just want to have them elaborate on that and whether trying to figure out whether they are using it in the same meaning. Stephen is pointing to Emma. So Emma, to what extent can we actually reconfigure the system, the craft?
So I know I used the word configuration. I'm not sure if I said reconfiguration, but in this case, the first thing that comes to mind for me is the static pictures that we see of the gateway, just like the International Space Station, are point in time where some modules may be docked in some orientations, but with the help of a robotic arm, you would be able to move modules around, redock them to allow larger vehicles, let's say, to dock axially or radially. That will be an important thing for us as we build up bigger and bigger at the gateway, have crew arrive in the Orion spacecraft, and the human landing system aggregate at gateway and go down to the surface and back up again. So, Stephen? Perfect.
In addition to that, that kind of reconfiguration, we also consider reconfiguration an unplanned change in the capability of the spacecraft. So that may be a degradation, it may be a failure, it could be a lucky thing where something works better than you expected, or you managed to integrate two things that weren't meant to be integrated before. That does happen on the ISS. Let's say you're driving your car, it's in a configuration. You have 4 good tires and a spare tire. You get a flat tire, you put the spare tire on there, put the flat one in the trunk, keep driving. You're driving a newly configured car. So any change that happens, we think of that way, on purpose or not. And by kind of categorizing it that way, we can think about state functions for the vehicle itself and the prognostic, the modeling for predictive cases. So the bottom line is a spacecraft is always being reconfigured, whether you know it or not.
And sometimes even before you launch. So I mentioned that our first two pieces are going to launch together. They will be integrated on the ground and launched in an extended fairing of a Falcon Heavy. That was not the original plan. The power propulsion element and our first habitable volume Halo were going to launch on separate rockets at separate times and dock autonomously. We decided to remove one launch them together, and now all of a sudden we are having to 180 degrees flip the orientation of the power propulsion element versus the standard way the commercial buses that it is based on launch. So tank design, all of that reconfiguration, absolutely.
A lot of engineering. Yes.
I could say one more thing about built sustainable environments on a surface, especially a partial gravity surface with big thermal swings, dust, highly radiation danger for humans. And that is when you see like concepts of moon stations or something like that, you have to ask, how did all those pieces get there and come together? Now, if we landed a bunch of pieces out in Nevada somewhere, could we autonomously send machines out there to put them together so that they were airtight? We don't currently even have that capability in Nevada. So it's a challenge anywhere we go.
Okay, I think we are about out of time, so I'm going to return the control to Sadia. You're muted.
So sorry. I think, Christy, you're closing this one out, please. Thank you so much, Daniel. Thank you, everybody on the panel.
You're welcome.
Yeah, and thank you from me as well. This was extremely interesting and informative from all the different perspectives. I'm super excited to see the system get up and running. I think it's going to be incredibly fun. So I think we do have a much clearer idea of what the challenges are as well. And I do think that, what we can learn from the station will tell us a bit more what we can do here on the planet as well. And I think in particular, the digital twin ideas are very timely and very relevant for many fields right at the moment. So with that, we'll close up this panel. We have one more panel that will start at 4:30, so at about a half an hour from now, on workforce development. So we have a bunch of experts from around Washington State with different perspectives on that topic. So again, you've got a bit of time here to do some networking, get up and stretch a bit, and I hope we will see you at 4:30.